Hello everybody, this is Yasmin again, solo doing a little bit presentation for ThatITShow. Welcome. Today what I'm going to do is I'm going to try and quickly go through the architecture landscape and start a series that is going to try to cover the processor that reshaped the modern processor industry. What we are talking about today is ARM. More specifically, we are going to be talking about all the reduced instruction set computers or processors being small, fast, and being something that completely changed how we did computing, and probably the kind of the processor and architecture that is going to reshape the future of the computing, because what they're doing right now is they're slowly taking over from the old CISC or complex instruction set computers. Before we even start, we need to start with the ARM processor, and we need to talk about how ARM came to be. The usual thing to do in the presentation like this is to start from the 1985 and say that in April 1985, the ARM microprocessors started actually appearing as the physical processor, because they were designed a little bit earlier and then they were shipped to manufacturing. And then VTI created processors and put them on the silica and delivered them back to ARM. And after a little bit of tweaking, they were able to display "Hello World, I'm ARM," and this is how the ARM architecture started being a physical thing. 3 micrometer lithography, 24,000 transistors, 24,800 transistors, and 1985. This is where it all started. But what I want to talk about more precisely is how the industry or the market or the landscape of the microprocessors looked like at that particular point in time. If you want to learn more about ARM, I suggest that you take a look at all the amazing videos that you can see from different amazing content creators like Retrobytes and all the other ones that I'm going to link in the description. What I want to do today in this short video is to try to go quickly and explain how we bridged the last 30 or so odd years, to be more honest, 40 years, and what happened between 1984, so 40 years ago, and today when it comes to processing, and how did the processing landscape change. So the ARM processor in this presentation is the main protagonist, and it was released in 1985. But while I was preparing this video, I was using ChatGPT to find out different additional data that I required about the processor industry. So I inquired it and tried to create the outlook and the breakdown on how the industry was looking like. What was the market like? What were the processors that were on the market at that particular point in time? And I must say that I was surprised, because I forgot that 8386, or 386 as it was known, was actually on the market at that particular point in time, because 386 was the processor that was used way later in the 90s. So actually I forgot that the timeline for the Intel and the timeline for the ARM are starting to connect when it goes from 1985, and that the first processor that ARM created was, as I said, relatively small, 25,000 transistors or so. It was huge based on the process and everything else. It was also 32-bit as the Intel, but Intel at the same time had something like 12 times more transistors, so transistor count is much higher in Intel. And at this particular point in time, Motorola 68020 was also present in the market. It was quicker than the Intel. It was a different processor, and the idea behind it was a little bit different than what Intel was doing. Zilog had Z8000, that was 16-bit processor, but it was also alive back then. There was the National Semiconductor NS32032. That was the first 32-bit processors to actually come to market, or one of the firsts. And its main rise to fame was that it defined some ideas that were later used in later processors by different manufacturers. So National Semi the processor is not something that we used a lot, or the industry was wasn't using it a lot, so it didn't take hold on the market. Western Design Center had something called 65C816, which was basically a 16-bit version of 6502 with additional instructions, and it was designed in such a way that they tried to keep the 6502 idea alive 10 years after the 6502 was introduced. And of course, we have the ARM1. Now, when I talk about ARM, I need to make a distinction. People tend to forget, or tend to confuse two things. One is the name of the processor itself. The processor that I showed you was called ARM1. The architecture was called ARMv1. And we are right now, we have reached ARMv9, but the processor itself is called Cortex something. And we are not going to talk about the processors too much when it comes to architectures, because I want to try to explain how the architecture itself was working. When ARM came to market, the processor market was pretty complicated. The early processors that started in 1975, in 1974 and so on, were processors that were trying to establish what a processor should look like. So neither Intel nor anybody else actually had any idea on how a processor should look like. They were just making things along. When Intel was designing its own processors, when 6502 was designed, when ARM was designed, in a way, people were trying to establish what the processor should look like, how it should behave, how the instruction set should look like, and a lot of different things. So basically, if you had a viable product, you could establish yourself on the market just simply by having a processor that is working. Right now, it is much harder for a small company like ARM or somebody else to come to the market. So this is the reason why we're not seeing so many different new processors. The only players that can introduce new processors right now are probably either big ones like Google or Meta, which are designing today's processors that are more or less designed specifically for AI, or NVIDIA, that is able to introduce processors simply because it has the market share when it comes to GPUs. So the GPUs themselves created the behemoth, and then NVIDIA is able to invest billions of dollars needed to create a new processor. So it's much harder to gain an entry into the processor industry right now. When we take a look at how the architecture was designed, we must first talk about how ARM works and what ARM does for its living. ARM is specifically not the company that manufactures processors. What they're creating architecture, they're creating know-how, and they're selling intellectual rights and architecture as a property. So, for example, when Apple wanted to create their new chips, or the entirety of the chips that Apple is right now using, because the M1, M2, M3 obviously M4 and so on, are not the only ARM chips that the Apple is using. They went to ARM and asked them for help for creating the new processors. So all the A processors that are powering the iPhones, iPads, and so on, and all the different U's, T's, R's, and so on that Apple is using right now for different processes and different devices, they were all created in part by just using the ARM architecture and the ARM technology, and then building upon it and creating a new processor. This is the functioning model that ARM was always using, and it is using right now. So what they're doing is they're releasing a cookbook, basically. They're telling the manufacturers how to design a processor, how to create a processor that has a particular set of instructions, and how to integrate those instructions and this silicon into something that can actually do something useful. And they have been doing this for the last 40 years. So they have come a long way. And if you take a look at the release dates or release years for the different architectures, you can see that for the first couple of architectures, let's say for the first 6 or 7, ARM wasn't so quick to introduce a new entirely new architecture. But what they did, and when they did it, they introduced the new architecture that included new features and enhancements that portray what was popular in the market in this particular moment. For example, ARM v5 introduced support for Java bytecode. So the processor itself was able to execute Java directly from the bytecode. And this was something that was extremely useful when it came to creating a new processor, because different systems that were on the market way back then weren't able to, for example, support Java directly. They had to do it through the software. So however you design the processor is going to always be faster than trying to do it in the software. And this was what ARM was trying to do. Later, when introducing new technologies, new architectures, ARM slowed down significantly. So there was a difference. For example, in the V5 to V6, the difference is 5 years. V6 to V7, difference is 2 years. Then we have a huge gap, being 7 years. And then ARM v9 was introduced 10 years later. We have those, let's call it minor revisions of the architecture, so v8.1, 0.2, 0.3, 0.4, but they didn't do too many significant changes. They were just either supporting existing functions and features and enhancing them, or they just improved some security capabilities or virtualization and something. And this was the idea, was just to make it more current and to keep up with whatever was on the market. V9 was introduced a couple of years ago, and V9 is mostly targeted towards servers. So V9 is something that is not of too much interest to us today, because what I want to mention and what I want to talk about is the ARM itself. So having said that ARM is not strictly producing the processors and just selling the IP, how can ARM be so important in the processor market? The thing is that when it comes to processor market, what we had was that somewhere in the 80s, during the start of the 80s and then the middle of the 80s, we had a couple of processors that were designed and that were coming to the market, and they could be roughly divided into two completely distinct groups. One was the CISC group, so complex instruction set computer, and the idea of the CISC group was to if something can be implemented in hardware, it is going to be implemented in hardware. So you had different instructions implemented As you can see in this slide, I tried to go over the instruction count for different processors. And as you can see, when it comes to x86 or the first couple of processors in x86, they had a couple of hundred instructions. But quickly, the number grew to over 1,000, then to over 2,000, then to 3,000 plus, as we have today. The reason is that if you decide that you are going to be doing a CISC computer, you are committed to doing everything in hardware, and you are trying to do different instructions that are going to do different things, however complex they are, in hardware. So, for example, modern Intel processors are able to decode and encode video. They are able to decode and encode audio directly from the processor itself. In contrast to this, RISC, or Reduced Instruction Set Computer, was designed from the start to be much simpler. The idea being that if you have a smaller and simpler CPU, you are able to get much more out of the existing architecture, or to be more precise, out of existing technology, because you can reuse the technology that is cheaper. In the example of 386 against ARM1 or ARM1, you can see that the transistor count was 12 times lower when it comes to ARM. And this means that they were able to use the older technology, and also that at any given time, if using the same technology as the leading processors of the age, they were able to squeeze out much more performance, because they could use the additional transistor count to create caches and to do things differently so that the processor itself is quicker. So on the right hand side, or the right hand column, you can see that ARM instructions, when it comes to comparable instruction set or comparable architectures, for example, in 2010, was 8 times smaller than the x86 instruction set. Then, with introduction of ARMv8, the instruction set for the ARM grew significantly, but it didn't continue to grow the way that x86-64 was growing. So right now we are talking about basically 1 to 2. So the ratio is that we have double the amount of instructions in Intel's processors and AMD's processors compared to what ARM is doing right now. Having said all this, the instruction set itself doesn't tell the entire story. Instruction set just simply says that when you are trying to create a application or something that can be run, we are going to have one of two distinct cases. First, if we're using the CISC, we are going to be having the compiler in charge of trying to translate as many as possible higher functions that we are doing in C, C#, Python, or whatever, into the appropriate instruction when it comes to Intel's processor, or whatever the CISC processor is underneath it. So we are going to end up with very specific and very the architecture dependent binary, or we are going to be having to create different binaries for different versions of the processors. Right now we have we can go even as far as 8 generations of Intel's processors, also the AMD and the related processors. So I'm talking about x86. So creating something that can be compiled and that is going to run quickly on all those processors is either going to be huge, so this is the size is going to be a problem, or the optimization is not going to be perfect. Because what you're doing is you are creating an instruction set, you're creating an application that is going to just utilize some of the instructions of the modern processors, since the older processors don't have those instructions. So either you create a separate version for every generation of the processor, or you try to go with what you have and do the common denominator, so the instructions that can be run on any processor that we have. This is a trade-off, and as the trade-offs go, this is one of the bigger ones. The ARM is not changing those instructions too quickly, so when we are talking about things that compile for the ARM, usually the compiler has to do a lot more thinking, because it needs to substitute a lot more commands as software libraries, and it needs to do a lot of compiling of various units that came with the processor itself. But at the same time, the optimization is there. Also, when it comes to ARM, the ARM was from the start designed and used by devices that were much more specific in their use. So while Intel was trying to create a general purpose processor that is going to be running, I don't know, both Windows and Linux and whatever, that is going to be running the laptops, desktop servers, and that kind of machines. From the start, ARM was more oriented towards being used in specific devices. For example, mobile devices like mobile phones or tablets or something else, starting with the Apple Newton way back then in the 80s. And since it was targeted specifically for specific devices, the optimizations that the ARM could pull off were much better and much more suited to a particular device. You didn't create a general purpose application. You created applications for the devices that you had. So almost in its entirety, the applications designed for the particular device were running much more smoothly on a given device, since all the optimizations were there, than the counterpart that you can run on PCs and in Windows, simply because the optimization was much more complex when it came to x86. So now we come to this slide, where I was trying to see what are the numbers and what is the percentage of the market that is done by the or that is used by the different manufacturers or different architectures. The thing here is that when it comes to market share, what we are used to is that we think that usually when we're dealing with the desktops and the laptops and the servers, we think that Intel is everywhere. And this is true when it comes to the market of PCs and laptops. Market share right now, and this information is coming from the ChatGPT, so this information is partially correct because they can be off by different numbers, but I specifically wanted to have this information on the screen before you to be able to talk about it and try to critically analyze what is here. So when it comes to PC and laptops, ChatGPT says 75 to 80% of the market. I would say that the market share is even larger because ChatGPT tends to overestimate how many or how much processors are being based on the ARM architecture right now. This is simply because they are overestimating the Apple's market share, because when it comes to PCs and laptops, the market share that the ARM uses in the laptop space and the PC space is almost exclusively based on what is happening when it comes to the Apple's lineup. So Apple's laptops are exclusively running on ARM, M1, M2, M3, and so on. This is the Apple's version of the RISC processor. And they are the main and dominant force when it comes to getting the share of the market of the PCs. There are some other devices like Surface, some versions of Microsoft Surface that are using the ARM processor. Microsoft has introduced the ARM desktop called Project Volterra, but the thing is that this is not something that is gaining the market as quickly as Apple is. So right now, when it comes to non-x86 computers, Apple is the main player. x86 is right now extremely dominant. So 80% or 90% of the market, which is probably more like it, is something that is extremely dominant, and especially in the server market, where almost in the entirety of the traditional enterprise and cloud servers are based on x86. This is something that is not going to change quickly. The servers are specific even more because they have an extensive software ecosystem. Or to be more precise, right now the servers are almost entirely based on AMD solution, Intel solutions, primarily because of the virtualization capabilities and different things that people are used to. Having said that, Linux has been compiled for the ARM. Linux has different versions that are able to run on the ARM processor, and almost everything that is available for x86 on Linux is also available for ARM. So switching the server user base over to ARM is not something that is as complicated as switching the PCs. PCs are still dominantly tied to Windows, so you are going to be needing to switch not only the OS but also all the applications, and those applications don't have their counterparts in Linux. When it comes to servers, the software ecosystem is much easily ported over to ARM, simply because the Linux and the everything that Linux supports is already supported under ARM, and Windows support right now is, I wouldn't call it non-existent, but it is not wide enough to support the enterprise. The remaining market share when it comes to processors is the ARM, and this is the 95% of smartphones. This means that almost everything other than the PC and the laptop and the server is going to run ARM. And usually not a single ARM processor, but multiples of ARM processors. So you're going to have both the main CPU, the GPU, the communication chips, and so on, based on the ARM architecture. And this is running everything from iPhones, Androids, iPads, all the different tablets from all the different manufacturers, and so on. And this is something that is an enormous part of the market. Also, embedded systems. Everything based on it says here from automotive system to home appliances, but also headphones, toothbrushes. There is actually a toothbrush that contains an ARM processor. So different devices that don't even require a processor are going to have an embedded system based on ARM, simply because the ARM is so cheap and so easy to implement that sometimes it's much easier to implement a processor instead of a microcontroller. Also, the thing that we need to mention is that right now there are also some older architectures still available. PowerPC is one of them. PowerPC is used in automotive and in some applications that require formally verified or extremely available systems. So they are hard to get rid of. And also PowerPC is available when it comes to high performance computing, simply because that some of the specific applications that high performance computing is using was written for the PowerPC, and the porting of it to another architecture is probably something that cannot be done simply. Now, the thing that I want to talk about also is not this thing. The thing is that I want to talk about is that these numbers, we are talking about the part of the market that is based on the number of PCs and laptops and based on the numbers of mobile devices. But when it comes to actually absolute numbers, so actual numbers that cover how many different processors are out there right now, ARM has probably over 90% of the entire processing power on the planet. Simple reason is that there is much more mobile devices than there are PCs and laptops right now. The number of new devices that are iPhones, phones, Androids, and so on, every year is numbered in billions, and the number of new PCs and laptops is in hundreds of millions. So the number of devices that are using the ARM processor is much, much, much higher than the number of devices using any other architecture. And this makes the ARM predominant force when it comes to processing. And this is not going to change. Right now, ARM has proven itself as the architecture that is able to do a lot without using a lot of power. And Intel is doing the exact thing that nobody expected for it to be doing, and this is trying to lower the power by using the same architectural changes that the ARM was implementing pretty long ago. So right now, I don't, and nobody's expecting the Intel to quickly corner the market when it comes to computing, the way it was using the market in the last 20 years or 30 years or so. And what is going to happen is probably that the ARM itself is going to be gaining even more. When it comes to market volume, there are some, I would say, breakdowns or typical sales for a given year. Is that global PC market is usually shipping something like 250 to 300 million units annually. And when it comes to PC market, this means that if we are taking into account that, let's say, 10 to 15, or as the ChatGPT says, 20%, this equates to something like 40 to 60 million units being based on ARM. I think that this number is too high. And I think that ChatGPT is counting it too high, because I don't believe that Apple is actually shipping 60 million units per year when it comes to PCs. I know that they're shipping much more when it comes to iPhones, but the PC or the laptop part of the Apple is probably not shipping 60 million units. Even when we include the laptops and Chromebooks, which are also running ARM. But when it comes to the number of ARM processors that are shipped outside of this thing, we are talking about billions. And we are talking about billions this for the simple reason that the typical ARM processor is extremely small. It has a few cores, but it is designed to be a CPU. Then you have additional cores that are designed to be performance CPUs, so faster cores that are able to do more. Then you have additional cores that are able to do the communication for Bluetooth. Then you have additional chips that are able to do Wi-Fi. Then you have LTE chipsets. You have Bluetooth that is low power. You have different GPS, different sensors, cameras, and so on, also running on different ARM cores. So your typical laptop, or your typical mobile phone can run as many as 20, 12, 13, 14, 15, 16, up to 20 different types of different cores and different types of cores. So what you're using in your hand is something that is extreme multiprocessing machine, and it's all based on ARM. So ARM is usually shipping a lot more cores and a lot more processors in a single unit than what Intel ever would, and this is the reason why ARM is so big on the market. Now, what we can expect in the future is probably that all the processors are slowly going to go in the same direction, because what Intel is doing and what AMD is doing is they're trying to come to terms that the modern computing requires smaller cores and faster cores that are able to do a little bit less but much faster. So basically, they're trying to switch from CISC to RISC, and they're trying to lower the instruction count per core by creating performance cores and power efficient cores. And this is something that is going to be probably following the same idea that ARM and the other different RISC providers have been using for years. And with that, what is going to happen is that we are going to be seeing a lot more similar processors or similar architectural ideas from Intel that we have already seen in ARM. What is ARM going to do, we actually don't know. They're probably going to stick with the idea that they have right now because this is a winning option. They're going to be upping the core count, and they're probably going to be targeting new cores that are able to run much quicker, so over 4 gigahertz when it comes to single core processing power, because this is the only case in which they are not as good as Intel is doing, so raw processing power. Although at the same time, everybody is probably going to go on the AI bandwagon, and ARM is not going to be the one to stay behind. So ARM is going to be doing the machine learning course, going to be doing the AI course, and so on. And they're already doing that. So we know that we are going to be seeing much more processors coming from them that are going to be able to do the AI natively and on the device. Okay, so with this small and quick presentation, I want to just start the ARM series. What you can expect from me next is going to be a little bit of ARM v7 assembly, and I'm going to do it in a couple of episodes where I'm going to try to teach you how to quickly come up to terms with what ARM is doing, how ARM can be programmed, and how you can actually learn how to do some assembly on ARM and how to do development on ARM. Because ARM itself is a little bit specific, since it is designed in such a way that everything is run inside the processor, and the communication with the memory is kept down as much as possible in order to create a bit better performance ratio, better performance when it comes to processing. But this is going to happen in the next episode. Until then, I'll see you. Bye.